Yeah, I'll start with a model that is probably familiar to most, unitary time evolution of a quantum density matrix. And so if you've seen the density matrix formulation, you've probably seen the unitary applied by conjugation, and would also have seen the unitary as generated by a Hamiltonian. In quantum information, of course, we also like to compose elementary unitaries to form larger unitaries that we call quantum circuits. And in truth, these models are equivalent up to some identifications. Usually in the gate model, we would start with some small set of unitaries that is universal in being able to approximate either Hamiltonian time evolution or a set of general unitaries in Hilbert space. And we often study the complexity in the sense of how much time or how many gates are used to generate a certain unitary or simulate a certain process. However, in quantum information, we also often consider time evolution of open quantum systems. And so here, the way that we would think about it is simply consider the system in the context of some environment. And so we would start by tensoring on usually some kind of initial state. The state here doesn't actually matter that much. And I mean, the input does, but the environment state, you can basically start with any pure state and get the same dynamics. Then we time evolve the whole thing unitarily as though it were a closed system and trace out the environment. And this leaves us with an output density that is evolved according to a quantum channel. And so this is a process that maps densities to densities. It is physically reasonable, but it's not unitary, and it's not unitary because information can be lost to that environment. So it's often non-invertible. Now, open quantum systems will often tend toward a couple of regimes. So one of the common things that happens when you expose a system to its environment is you'll see a lot of randomness. This will cause decoherence, it will cause mixture. But we also observe quite commonly in life that there are systems that behave classically, and so that appear decohered, that don't seem to maintain their quantum aspects, but nonetheless appear deterministic. So this is a pendulum. A pendulum follows very clean deterministic dynamics for a long time, despite the fact that as a quantum system, it would be undergoing what we presume to be very strong decohering noise. And the third regime that I'll mention today of interest is when, in some cases, we may actually see that the system maintains its quantum aspects and exhibits certain complexities that we couldn't obtain classically. So there's been a lot of history around the distinction between quantum and classical objects, especially in the recent news. There's been some very famous experiments to try to rule out classical hidden variables or classical simulation models of quantum mechanics. But what I'm interested primarily is in what happens to these regimes as systems scale. So when we take a quantum system and we scale that system up, say a many-body system, where does it go? And in particular, why is it that if we observe quantum dynamics at the microscale and classical dynamics at the macroscale, somewhere in between, it looks like we're seeing randomness. So you take a quantum computer, you scale it up, and today what you would see is that it's going to be probably noise dominated. And after a certain size and depth, you'll mostly see random outputs. Yet in natural systems, we nonetheless get some kind of determinism without having to explicitly or artificially protect or correct anything. So this talk will be in 3 primary parts, or maybe 2 primary parts. First, I'll talk some about quantum classical complexity, then about noise, and if time permits, possibly about some results on how some of these distinctions could emerge from timescale separations. So I often look to ideas from quantum information and quantum computer science in understanding physics. And on some level, a computation is a physical system. We start by engineering some physical systems dynamics. Maybe the physical system is like the MacBook, and that will encode some kind of an input state. We let it time evolve, possibly under also engineered equations of motion. And then we measure information about its final state, and we get an output. And usually these would be modeled as binary strings in computer science, whereas from a classical physics or quantum physics perspective, we would use words like initial conditions and observations. Conversely, physics often seem to act like computations. So if we take, for example, entanglement in systems of quantum matter, this has become a very big topic. Entanglement entropy is now very common in various areas of physics. And these often use ideas that came from quantum information, ideas like entropy, ideas like local operations, or communication complexity even comes up in these settings. Of course, there's the well-known analogy now between black hole physics and models such as random circuits or other models of quantum computation that would give you the same sort of quantum chaotic behavior that we expect to see from a black hole gravity duel. And so quantum or computational complexity asks how much of something is required to compute certain functions, generate a physical state, or otherwise undertake a process. And this notion is fairly broad. You can talk about time complexity, you can talk about space complexity. Here, I'm going to primarily focus on the complexity of generating samples at the output from something. So this is less commonly considered in high energy physics, I think. Usually you might think about the circuit complexity of creating a state. This notion is a little bit weaker in the sense that we are looking at something with a classical output. And so it is probably in some sense easier to achieve this kind of complexity. But in general, when we're thinking about complexity, we're thinking about how resources scale up as functions of n, which is a system size, or possibly some parameter that controls how much we put in at the input. So we had to take n bits, and of particular interest is the question of, does the complexity of the process scale polynomially or possibly exponentially, super polynomially in n? Now, from the computer science perspective, there's a hierarchy of complexity classes. So P refers to the problems that are usually considered tractable in polynomial time. This is what we usually think of as being reasonable to compute in practice, although there's some fuzziness in how practice and theory match up here. You could have large constants, for instance. BPP adds randomness to that. It is not known whether BPP and P are the same complexity class. BPP is going to be at least as large. It's sort of giving the computer some extra resource in having random computation, but also allowing some error at the end of computation. BQP is what we think that quantum computers will be able to do. And I'm just going to put NP here. You've probably heard of P versus NP at some point. This is another complexity class that's very famous. We don't actually know any of these relations rigorously. It could be that these are all the same complexity class. If P equals NP and BQP equals P. But it's believed that at the very least, probably BQP and NP are not comparable. Neither one is contained in the other, and that neither is equal to P. Whether BPP equals P, I think, is more of a question.
In the definition of BQP, do people include probabilistic, like
Yeah, so
probabilistic quantum computation is the
it's bigger than BPP, and in theory, you could ask about exact quantum computations, and sometimes there's nice mathematical structures, but that class is usually not studied because it is not believed that one can really control a quantum system exactly. So usually we would say that something is in BPP if we can achieve it with a fault-tolerant quantum computer, in which case we can make the error rate smaller by spending more time and more qubits, but we can never actually get it to zero.
But yeah, the errors die away at n, right?
Yeah, so there is a sort of scheme in which you can say, I mean, there are some, if you want to think about like really fine-grained complexity, I think there are some unappreciated questions in here, such as whether there is really a linear scaling between the number of qubits you need and the size of an input, because it could well be that you also then need to spend extra qubits correcting errors, and you need to think about like, is the layout of this thing constrained by 2D or 3D space? That could matter. And those could add little overheads. And in truth, that's true of a lot of complexity things, like technically things that we think have order 1 time might actually be logarithmic, like integer addition, but we just don't consider that. I would say that these classes are believed to be robust. So like P is all polynomial time. And so if you have like an extra factor of n because your computer is one-dimensional and it has to walk the information back and forth all the time, that won't actually change the definition of P. And in fact, I'm going to jump ahead and mention this. So there was
naively, but in that diagram, there is also something outside.
Oh yeah, I mean there's something called the complexity zoo. If I really wanted to, I could draw like hundreds of circles on this with different classes. There's RP, there's P space contains the whole thing. And then it's known that exponential time is bigger than this and contains it. So yeah, there's like no limit on how much you could put. I restricted to the classes that I think are reasonably close to quantum and classical. So
Another thing, it's not known whether BQP is strictly smaller than QMA or something. There's not known.
yeah, so there's QMA, which would be bigger than, which would contain both BQP and NP.
Yeah.
But yeah, I don't think that it's known whether. In fact, what I would say is that you could wrap like all of these classes in P space, and we don't know whether P space equals P.
Well, yeah.
So complexity theory separations are famously hard. And one of the ways to sort of note that it's hard to prove something about complexity is to note that it would imply that P is not equal to P space. Because even that's really hard. And if you want something even harder, you can try to solve P versus NP. That's a fun thing to try if you're bored. So the extended Church-Turing thesis is building on what's called the Church-Turing thesis of Church and Turing. And the Church-Turing thesis said that all reasonable models of computation that are sufficiently universal would be equivalent for computability. So in other words, you could simulate any physical or reasonable process on a Turing machine with some arbitrary amount of resources. And the extended Church-Turing thesis said, well, not only should it be in principle doable, but it should be polynomial overhead. So a classical Turing machine would be able to simulate any other classical computer, maybe with some extra factors of n, some extra powers. And this had held up pretty well. These are some different historical computing devices, a Babbage engine, I believe, a mechanical computer. This is a vacuum tube computer, which was early electronics. And this is, of course, a fairly modern computer, though it does have a floppy drive. And one of the proposals of quantum computing is that this actually would not extend into the quantum computing area. That BQP not equaling BPP means that there is actually a more powerful, physically realizable model of computation. And I will note briefly that the word complexity is a multiple entendre in physics. We also have complex systems. It can be used to refer to like chaos and nonlinearity. But I won't go too much into that here. So to model an idealized quantum computation, we would write down a formula like this in many cases. We have an input state, some unitaries. This is a circuit, and measure it. In this case, measuring it to actually get a bit string out. And this actually has quite a bit of structure to it. So each of these unitaries is linear. And then when we multiply these unitaries, we end up with some polynomial description of the circuit. So we can actually write these approximately using polynomials. And because we can write them approximately using polynomials, and largely because quantum mechanics has a lot of continuous structure on it that we wouldn't necessarily see in a classical binary model, we get polynomial interpolation, which says that if we can do a lot of computations in a neighborhood of some circuits or some inputs, we can actually extrapolate to other circuits or inputs in that neighborhood.
I have a basic question. What do you mean by continuous in quantum but not in classical case?
So in many cases, these unitaries are just, if we want to consider them in like full generality, these might be members of a unitary group, like maybe a unitary group on pairs of qubits, each one. And so there's the unitary group is, of course, a compact continuous group. In classical settings, it would be more common to actually restrict this to like some kind of discrete set of functions like and or and not. But in quantum, to get universal gate sets, there's usually some way of generating at least low dimensional unitaries that is continuous and at least approximates that compact group.
Nice, thank you.
And so that gives us a polynomial interpolation structure and what's called a worst to average case reduction, which implies that if we have say a very hard instance, maybe a circuit we think is very complicated, and we want to try to estimate what its outputs will look like, we could try to do that by sampling a bunch of circuits that are close to it, but seem simpler, and then extrapolating to the value we want. And this idea comes from a couple of papers. This is actually one of the things that Bill Pfefferman, who is my primary mentor at UChicago, works on. And one of the consequences of this is that guessing what these measurement probabilities are after a circuit has been applied to a simple input is probably typically hard. And the reasoning again is that if we could solve typical instances easily, we could polynomially extrapolate and solve instances that we think model classical problems we shouldn't be able to solve. So things that we don't think are in P. And so this doesn't just apply to quantum circuits, it also applies to Hamiltonian models. If a Hamiltonian has sufficiently expressive, and we average over some parameters of that Hamiltonian, we will often find that typical instances do not appear to yield classically simulatable measurement results.
So when you say polynomial extrapolation, what does this extrapolation mean, like, mathematically?
Yeah, so there's a algorithm that takes a bunch of input and output points with the assumption that these come from a polynomial of a certain degree. And if these fall within certain error bounds, so not all of them have to be exactly right, then it can estimate the value of a different input to that polynomial.
I see.
And that's because polynomials have a lot of structure. They have a lot of analytic structure to them,
Right.
and also geometric structure. So as an example of what we get from this, if we take something like an SYK model, which is a model commonly used in modeling quantum chaos, is a sort of simplified analog of quantum gravity and black hole physics. These actually appear to exhibit classical sampling hardness. And so if you use an SYK model as your computer, and it was actually a physical SYK instance, this would be very hard to simulate classically in principle. And not only would it be hard, it would be hard sort of in a typical way. That if you just kind of took some instances of the model and put inputs into them and sampled outputs, within a few tries, you'd probably get something that you couldn't have easily gotten from a classical computer. And so this leads to a question of whether systems in nature might actually naturally witness violations of the extended Church-Turing thesis. So I could imagine a sort of hypothetical protocol in which I took an input string, encoded that in some matter, maybe as a spin ensemble, dropped it into a black hole, went and measured some of the Hawking radiation, and then asked, well, is this something that could have been computed by a classical process of comparable size? And of course, a black hole being a very large system in many cases, comparable size, incomparable size would mean that for a classical computer to do that, it would be possibly like larger than the universe or some other really ridiculous scale. So it might be that some of these complex systems are actually behaving in ways that would not be possible to simulate computationally if they were classical.
So I think I missed something. So in the extended Church-Turing thesis, it was about whether you could simulate this classically.
Yeah, so this originally,
Universal classical computer or quantum?
so this originally said by other universal computers. And so the idea is that the quantum computers actually kind of break this. They say that there are universal classical computers, and these are less powerful than universal quantum computers.
So when you said violation of extended Church-Turing thesis, you're talking about classical computers not being powerful enough to create a typical instance of SYK.
Yeah.
Okay, so the classical one, because there's one that's called like,
So
there's another one that uses quantum VQ.
yeah, there's the quantum extended Turing thesis,
Yeah.
which we don't know of anything that looks like a violation of it in this world.
Sorry, I just
Although it actually has been proposed on occasion that maybe black holes actually violate the quantum version as well, and that you couldn't simulate them on quantum computers. But that's a more, I think, more questioned conjecture. People don't really have a sense of whether that's true. And I think the usual take on it would be that they probably are not more powerful than sort of a quantum computer of the same mass, say. So there is, however, a catch to this, which is that to get this hardness result and to get it typically, one usually needs extreme accuracy in the estimates of these probabilities or in the matching between sampling from the simulator and the actual quantum process. And so if you allow some reasonable amount of imprecision, it might actually be relatively easy to kind of fake something like SYK using a classical computer. And that kind of brings up a problem, which is that, again, as pointed out initially, most quantum systems that we encounter, we don't have full control over. There's going to be noise, there's going to be decoherence. We're never really going to be able to draw samples from the exact model that we think we're looking at. And in fact, some of these experiments recently, even though they're often touted as showing in artificially engineered circuits, non-classical computations, are not expected to scale now. It's actually expected that you get very good results in certain ranges, and then as you scale up, you run into other barriers. And so a lot of the evidence for sort of scalable non-classical computation is not necessarily going to hold up as you try to go to asymptotics. And so this would not necessarily rule out the extended Church-Turing thesis. But there's also the fact that we see a lot of macroscopic classical systems. We see a lot of macroscopic classical determinism. And meanwhile, we're seeing randomness in quantum computer outputs typically. In principle, this would be saved by engineering in fault tolerance. And so if we could error correct things, and we could error correct things well enough, we should be able to reach a regime in which the quantum computer is doing things in a more deterministic, less noisy way, and eventually accessing the full power of BQP. But we're not there yet. And it's also a question of, well, okay, maybe this works in the lab, but do we ever see this in natural systems? Is this something that is like completely artificial? And if so, why is it, like, why are we so special in being able to make this? And so one could posit that because of noise and because of uncontrolled interactions in the universe, even though there is quantum complexity in the exact dynamics, or at least in the idealized dynamics, we never actually observe it. We're always going to see noisy versions that will look like they could potentially be classical from a computational perspective. Now, this doesn't necessarily apply to something like a Bell test, which is using a different test, but it is possibly saying something about scaling up of quantum systems, that the universe is making it hard to scale up non-classicality. And so this is where we get into the second part of the talk on noise. And so what do we actually know about noise? Well, this is a very common way of modeling noise. It's Lindbladian. It's an open system generalization of the Hamiltonian, kind of like how the channel was an open system generalization of the unitary. And you actually see that this does solve a differential equation. If you were to just keep this part in blue here, this would be the Schrodinger equation. But now we've added this stochastic or incoherent part, which again lets it act irreversibly, non-unitarily, which models interaction with an environment. And so this is what we call a quantum Markov semigroup. Often this will have a subspace of invariant states and decay things toward that subspace. We might think of that in many cases as like an equilibrium space. And in fact, you can use Lindbladians often to model thermal systems. Sometimes there will still be persistent rotations in that space, but I'm not going to go too much into what we do about that. And
Yeah. So, but in terms of the spectrum of Lindbladian, to have this fixed point projection as a limit in time, you want the spectrum of the Lindbladian to have no, except for the invariant points, invariant operators, you want no phases, right?
yeah,
Is
so
the intuition that that's typical? Because that sort of is counterintuitive to me.
yeah, so I think the intuition is that that's typical, and it's all actually very closely related to why BQP is defined with error bounds and not with perfect computations. That it is extremely rare to find a system which is really exactly unitary.
But but you could have quantum channel with spectrum on the magic with phases in spectrums. Right?
Yeah, so that would imply that there's some subspace on which it's acting reversibly, right?
Right, exactly.
And so I think it is actually believed that that would be exceptional.
Oh yeah. That's right.
That you really, can really do it an infinite number of times, no decoherence, no loss, like perfectly isolated closed system.
So I guess you're saying it's unstable. If I just perturb it by a tiny bit, perturb the Lindbladian, I expect all of those guys to move inside of this.
Yeah.
Wow.
Yeah, so that's kind of a good mathematical reason to think that that would be atypical, that under small perturbations, you just lose that aspect. Sort of arbitrarily small noise will eliminate it.
Yeah, thank you.
So one of the tools or metrics that we'll use to study this is called the relative entropy. This is a quantum generalization of the Kullback-Leibler divergence. And I could go a lot into what this arises from, but in terms of why we like this, it's an upper bound on various notions of distance and quantum resources that is a monotone under quantum channels applied to both arguments. And I would say that we will often treat this like it's a distance, even though it is not symmetric in its arguments, and so it's not a true distance. And what we often want to study is the relative entropy of a density with respect to its fixed point projection. And so the type of inequalities that we prove on this are what we call modified logarithmic Sobolev inequalities, which is showing exponential decay of the relative entropy under the action of a semigroup. And then we have this complete version, CMLSI. And the complete version says that even if you extend by some auxiliary system and assume that the auxiliary has no noise on it, you would still get this exponential decay. And so what this really is doing is it's tensor stabilizing it. It's making it so that you can take CMLSI estimates for subsystems of a composite system and put them together to get an estimate for the whole system. And so this, again, it upper bounds notions like diamond door norms and fidelities. And so you don't have to stay in the relative entropy world. You can actually get a lot of different ways of characterizing state decay from this. And
So just to understand this. So phi is a semigroup.
yeah, so phi t is a semigroup.
And that curly epsilon is the limit of t going to infinity of it, right?
Yeah.
And lambda is like is it the lowest the smallest eigenvalue of the Lindbladian?
So this is an MLSI constant. It is related to the spectral gap of the Lindbladian,
Okay.
but it's not equal to the spectral gap. In fact, it's if you look at this projection will often be a von Neumann subalgebra or a conditional expectation. It will have an index, and this lambda sort of combines the spectral gap with the index. So if you understand those terms and those tools, you can get here, but that's probably for the more specialist audience.
So the larger the index,
Usually the larger the index, the smaller lambda is compared to the spectral gap. And so you could think of the index as saying how much work does this process have to do to decay the system. So as you add qubits to a system, the index goes up.
Right.
And that's because it could actually take longer to destroy all the information. So again, that's kind of the specialist way of putting it. But this is an exponential decay inequality on a measure of how far you are from fully decayed. If you're not familiar with indices or spectral gaps or Lindbladians.
I have a very basic question. So you mentioned about index. So this statement is correct for finite index algebra. If you have like some very bad algebra with the infinite index, is there a way to make sense of this kind of inequality?
You can make sense of it, but it might be false even if you have a spectral gap.
Okay.
So I'll get into a minute when we know this is true. And in particular, this is a condition known as GNS detailed balance, which says that the Lindbladian would be self-adjoint with respect to an inner product. And if you understand modular theory, it would also have to commute with the modular group with respect to the state omega. And if this has detailed balance with respect to the trace, that's equivalent to self-adjointness. And now one thing that detailed balance does is it actually ensures that you do have this fixed point projection. But maybe more non-trivially, or more interestingly, if you're in finite dimension with detailed balance, then you have exponential decay. There is CMLSI for all such systems.
So can you go one? So you say that the self-adjoint quantum channel has detailed balance. When it commutes, it means that kind of confused. So the stuff that commute with the modular group or the centralizer, right?
Yeah.
Is there a way of understanding the quantum detailed balance in terms of the centralizer? Or maybe ask differently, when you say when it commutes, is there some sort of if and only if situation, or is it just if?
So if it commutes with the centralizer and if it is in the centralizer and it has this it's self-adjoint with respect to this inner product,
Yeah.
then it has detailed balance. I don't actually recall what the converse is, if any.
Okay, thank you.
So this is a condition that yields universal exponential decay of relative entropy or universal CMLSI, not just MLSI, but we get the complete tensor stable version. And this was actually proven in a bunch of recent papers. But if you go outside the finite dimensional case, there are some other ways of deriving this kind of inequality, in particular by relating to CP order.
But can I ask another question about this? So this statement that you made, can I understand this in the following sense that if you have detailed balance, then the spectrum of your Lindbladian is limited to a real line? And actually, it ends up being actually only on the positive half line. Right? Because detailed balance is just a conjugation in the spectrum.
Yeah, so I would say that that's probably right. But I think that so it took a long time to show that having a spectral gap implies CLSI or CMLSI.
And that has been shown with what assumptions about the index?
So in finite dimension, the index is always finite. This does not actually tell you anything about the constant.
Oh, I see.
So the index could give you a very slow decay rate, but it's still exponential.
I see.
And So in general von Neumann algebras, if you can find a CP order inequality, which is related to the order on matrices in the sort of large repetition limit, then you can find CMLSI for small number or for one instance or for short times. And so one thing that's nice about this result is it actually kind of at least bypasses using the index explicitly. And so this ends up actually being stable under generalization to the different von Neumann algebras, including the type 3. And this one is essentially saying if you know something about the very long time limit, then the Markovian identity structure lets you say something about the short time behavior.
You're saying that this is a general von Neumann algebra?
So this, yeah, I mean, these conditions are non-trivial. In finite dimension, these conditions are implied by detailed balance.
So
But
in quantum field theory, there are these type 1 algebra inclusions with trivial index. And those are very confusing. Anyway. Yeah. Okay.
yeah, I mean, I believe that this, you don't actually need to think about index for this. But you do need to think about this condition and what this means in a general, which is in type 3.1, this is very hard to think about. So it is kind of implicitly hiding the hardness of actually working with this.
I have
but-
a question. Do you assume phi to preserve omega, or you don't assume so?
So that is implied already by the GOS symmetry and detail balance.
Okay.
So yeah, omega is a fixed point invariant state.
All right.
So going back to the less technical picture, what usually lacks detailed balance are Lindbladians with a non-trivial Hamiltonian part. And so this actually kind of shows what detailed balance is. It's not a completely general condition. There are lots of very interesting categories of semigroups that have it, but there are also many that don't, especially including things that would come up in quantum computing or in things that would come up in dynamics of quantum systems. And so one question that actually has remained is whether there is some way of splitting a Lindbladian into a canonical dissipator, which is this part, and Hamiltonian, in which having a trivial Hamiltonian part would imply CMLSI. But that's kind of an open question. I would be very interested in any thoughts on that. Now, CMLSI is very good at explaining situations in which we separate the noise from the coherent dynamics. Yes?
So can you go one slide back? So I'm probably making a mistake, I'm being naive, but I just want to understand why is this wrong? So if I think of this in the GNS overspace, I have an operator, I have it's a the generator of the contraction semigroup. Why can't they just split that generator into self-adjoint and non-self-adjoint part? What's wrong about this?
So I mean, you can probably decompose it that way, I think.
The
That's
self-adjoint, yeah, the self-adjoint part would be the analog of this detailed balance. It will satisfy detailed balance. I guess you're saying that the part that's not self-adjoint is not clear.
Yeah, and so this is if the generators don't commute, then the semigroup you get can't be split into two semigroups.
And so in principle, this stochastic part is an approximation because it should always be with Hamiltonian or not.
Yeah, so I'll get to that at the very end, and I hope you'll be here. You may have to leave before I get to that slide, but all right. So yeah, this is good for explaining things like circuits. When you combine the coherent and noisy dynamics, you can get some really weird stuff. This is a paper that I wrote recently, and as an example, there is actually often a regime where if you sort of construct a Lindbladian where you can tune noise on different parts of the system, and you tune the noise on one part of the system way up, the information that's preserved is measured by the relative entropy, is going to rebound in the noise strength. And so that's one of the weird things that happens. You actually lose monotonicity in terms of strength of local noise and how it relates to full decay of the system. CMLSI breaks down in many of these cases. That's probably good news and what we expect for like quantum error correction. And nonetheless, though, you do get exponential decay after some amount of time. And so we still do get a sort of CMLSI-like theorem, but now with this finite timescale stuck in, where the rate depends on the timescale. And what this is reflecting is that the breakdown in decay is actually for infinitesimal time. So if you set a sort of finite timescale, you'll get out of this regime and get back into an exponential decay regime. This also sort of implies that for quantum error correction, you really want to be fast. You want to run error correction before the noise has a chance to really build up. But what we saw before was that if the coherent time evolution is spreading noise around, then when the noise is extremely strong, the decay rate can actually be bounded inversely to the noise strength because the noise will induce xenodynamics. And so to explain this result, we can recall the Bloch sphere, which visualizes a qubit state. And coherent dynamics would rotate the state around an axis through the sphere, while noise would move the state towards an axis or towards the center. And here what we see is that if we want to, say, flip a state coherently, we'd have to go all the way around the edge. There's no coherent path that, say, goes down the center. And so if we had some kind of rotation, say about the X or Y axis when this is the Z axis, then near the beginning of that, the qubit state is moving almost on a tangent line to this axis. And noise that is bringing it towards this axis will actually directly counter the coherent movement. And so this will suppress dynamics of the system. It means that extremely strong noise can actually freeze a system rather than mixing it. And so this can actually be state preserving. Now, one of the next questions was, well, does this type of thing yield classical dynamics? Is this why we see systems that have no quantum coherent parts, but appear to act very deterministically that don't mix? And in this model, that's probably not the case. And the reason, again, is that we don't actually get dynamics here. We get complete shutdown of off-diagonal components in the early time unitaries, which actually ends up basically suppressing all dynamics eventually. And so we end up recovering classical statics. So that's going to lead to part 3, and I only have a few slides on this, but this is hopefully going to answer your question. You can stay for another minute. We usually like to think of Lindbladians as generated, again, in this system environment picture by a larger Hamiltonian time evolution. And here we would assume that the environment is very large, so it's capable of absorbing lots of information without sending it back. And it's dissipative, meaning that it quickly sort of takes anything it gained from the system away. It's not causing back action from the system state. But as it turns out, this model, if you actually look at what the early time expansions of this are, the initial eigenvalue changes in the density matrix are of quadratic order. This is actually a screenshot from a textbook showing that there is, if you add some off-diagonal terms, which is what the linear order Hamiltonian commutator would do, you'll get a quadratic perturbation to the eigenvalues. And so this is actually incompatible with small time MLSI. You don't get enough decay at those very initial times. And so the partial conclusion that I'll reach here is that semigroups are effective models. And if we want to understand better how things like classicality and possibly quantum complexity can be self-preserving, we might need to look at the more microscopic structure. Where are we actually getting the semigroup from? What are we ignoring or effectively integrating out in this model? And so I think that's where I'll end the kind of main part of the talk. For anyone who wants to ask questions, we have a little question period. And there is indeed a part that I could go into further detail on the board or sort of more informally. But this, I think, would end the recorded talk.
I do have one question actually. If you could throw a few slides back. This further, yeah. This one. So there's a competition between coherent dynamics and noise.
Yeah.
And so let's say I have a tuning parameter that will tune noise. Do you encounter setups where so there will be a transition as you increase noise, right? There's a competition between coherent dynamics and freezing and that noise, right?
Yeah.
Can you take some sort of a quote unquote thermodynamic limit to turn this into a phase transition? Right?
Yeah, so I think that's a really interesting question.
So something like Anderson localization kind of setup, where you increase noise until your state that are with finite wave packet spread end up freezing in time. They become they just evolve by phase.
Yeah, so we don't know whether the regime transition here is smooth or whether there is a real phase transition in the formal sense here.
Well, you'll have to have a large parameter to make it a phase transition, right? So like large entropy or something.
Yeah, so, well, even that is, what parameter you're making large is questionable there.
Kind of quantum system, everything is analytic, right? You're not going to get non-analysis with it. So.
Yeah.
Anyway, yeah, I think it's just very curious.
Yeah, so there is something interesting there. We don't know exactly what the, so we kind of understand this regime pretty well, I think. And then we understand this regime pretty well. And we don't really know what's happening in the middle, other than that there is a middle.
So for example, a silly example of this, or maybe interesting example, I don't know, is what if you add this YK constant term? Can you arrange for a phase transition? Over there you have a large N. Right? Can you make the noise term or the stochastic term compete with coherent dynamics?
Yeah, so certainly there's a competition, but whether there's a sharp phase transition is a new question. And it's one I could say a little bit more about, but maybe after.
Right. I usually thought that is a classical information that appears at the end, but you say no.
What do you mean by that?
Like you have the information, then part of it, like this, it seems to go to some fraction at the end when it goes up. So I thought maybe that distinguishes the classical information from taking the quantum system.
Yeah, so if you had a very strong dephasing noise in particular, then that would be true. And so I didn't go too much into what the model is for this. And in fact, you see this shape in several models. And that is the better or the sort of more historically known regime where you induce a Zeno effect. And it really is just a Zeno effect, where the noise is acting like a measurement, and therefore it's freezing the system completely. But this regime that is kind of more surprising when you see this is, so you take a spin chain and you overwhelmingly depolarize one end of the spin chain. You'll actually see this same kind of curve where at first what's happening is that as you're adding noise, it's spreading down the chain and it's mixing everything. And then when you hit this regime, it's suppressing the interactions. And so it's causing that one very heavily noised qubit to become isolated. And therefore the other 3 qubits are protected. And you actually can think of this as a kind of Zeno effect. It's a very sort of wide generalization of what we think of as Zeno effect, but there is this notion that there's adiabatic theorems that are essentially like Zeno dynamics, and even that dynamical decoupling, which is a noise reduction technique in quantum computing, is a little bit Zeno-like in how it works, maybe a lot Zeno-like in how it works.
Any last questions before we switch to the Boston part? Well, maybe Keisha, you want to start before?
Yeah, and I mean, I would say that, like, officially, I think the talk is over. So anyone who wants to head out or has to head out, please.